Make sure the sound is working. Yep, we're good. Okay, here we go. Okay, 13. It says we're supposed to use limits to show whether or not this function has a left half horizontal asymptote. So you need a flashcard like the one you see here. I put blue on the front, red on the back. So make that flashcard. I believe this will give you 5 total flashcards so far. Cool. We don't really have that many. There's just a few key items you have to have memorized. So. No, because the AP test doesn't allow any aids, so I've got to get you used to that. So yeah, I can't let you use them on the test. Good question, though. Okay, there would be a nearly identical card for a right horizontal asymptote. So if I were a student, I wouldn't make another card. I just remember, oh yeah, if there's a left, there's a right, and it's going to be positive infinity instead of negative. So if you want to make a second card, you can. But I personally would get by with just one. So, questions? Awesome. Okay, so we got to find a limit. So you're going to write on your paper the limit as x approaches negative infinity of this formula called f. That's what we're trying to find so that we can determine whether the function has a left horizontal asymptote or not. Cool. Okay, you need another card now. The front of the flashcard should say how to find a limit. The front of the card should say how to find a limit. The back of the card has those 4 steps listed. So front of the card, how to find a limit. Back of the card, steps 1, 2, 3, and 4. Oh, please, Sammy.
On step 1, is that a negative infinity or just a positive?
Oh, thank you. My pen's in the way. It actually applies to either. So if x is approaching negative infinity, you still compare terms that add. If x is approaching positive infinity, you still compare terms that add. So the card's not totally clear on that point, but it is either one. Good question. 2 more for Samuel. MC failing. Okay, so here we go. So this limit is x approaching negative infinity. So we are going to need to compare terms that are adding. Technically the word term means things that add. So the card could just say compare terms. But emphasizing the addition seems to help students, so I leave those words that add. Okay? So you look at this formula for f, and you simply raise your hand, and you tell me. Can you tell me any 2 terms that are being added in that blue box? Your hands. You can see terms. Term just means a thing. It's being added to another thing. This sign from Amanda Lindstrom is meant to help you remember that. It's just term is just a thing plus a thing. So can anyone see any two things that are being added inside that blue box? A little harder to see than I was thinking, but that's okay, we'll just talk about it. So if your hand is raised, give yourself a point. We'll try Davis. What two things do you see being added, David?
The ax to the third plus x squared.
So we need to keep the negative. I'll explain that in a second. You're doing fine. So we definitely have a negative 8x cubed. And then I think the best way to look at this is think of hidden plus signs. And then, so there's the yellow term plus the blue term. Okay? 3 points for Davis, please. So
What about 2 minus 5x squared
if I go up there, we could have a 2.
plus a
So if he's exactly on the right track, you have another plus sign in between, and that's being added to a negative 5x squared. Absolutely. So we've got a yellow term plus a blue, and a red term plus a purple. Perfect. 2 more. Please. Anna.
3x is 7 plus a x cubed.
So we could have the black term. Is this one you said, Anna?
Yeah.
Plus the yellow. Huh? For sure.
Do you think borrow some note cards for stats?
Oh yeah, for sure. Many as you want. Take 2 trays if you need to. See ya. Cut his hair, man. It looks different. So I didn't recognize him for a minute when he walked in the door. He had my class last year. Billy Shane. Yeah. Like, who are you? Okay. Are we good? Awesome. Okay, next step. You identify the terms that are added. The next step is pretty much just memorization. Well, in part, I guess. Let's do the easy step first. Let's look at 2 plus 5x squared. So if you're adding 2 plus 5x squared, and you are, sorry, negative 5x squared, and you're doing that for x's that become increasingly negative. So the x becomes more and more negative. Some kind of pattern like this, maybe. So the x is becoming increasingly negative. For this one, you're going to have 2 plus negative 5, and then the x is negative 1. Let's see, and that's squared. So that's really going to end up just being negative 3. So the negative 2, so the 2 and the 5x squared both contributed significantly to the final result. Does everybody understand what I mean so far? Okay, I took 2 things, added them together. We both made a contribution to the final result. However, when we get all the way up here, like a million, we got 2 plus negative 5 times 1 million squared. Sorry, negative 1 million. I do not know off the top of my head what 1 million squared is, but I know it's really, really big. When I add 2, I'm not really going to notice much. The 2 is going to make a very insignificant contribution to the total. Questions? So the point is that as x becomes more and more negative, this 2 becomes less and less important in terms of finding the total of those 2 terms. Questions? So what we can do is we can ignore the 2. But only if x is becoming more and more negative. Or if x were becoming more and more positive, the same result would occur. We could ignore the 2. That means when we write the next line here, make sure you put equal. And you're still finding a limit as x approaches negative infinity. But now, the limit formula we're working with becomes quite a bit simpler, because we don't have to worry about that 2. We can just write negative 5x squared. There's more to write, but we'll pause there for a minute. Anyone have a question about why it was legal and logical? It's got to be logical to you, otherwise you won't remember it. Why it was logical to say, don't really need to worry about the 2.
So when we got rid of it, because it just didn't matter that much?
Yeah, the idea is that you're really trying to figure out what is this going to equal as x becomes more and more negative. And as x becomes more and more negative, this half of the total gets larger and larger and larger, so the 2 makes less and less contribution. So in the limiting sense, the 2 is unimportant. Good question, 2 more. Anything else? Oh, please.
Why did we pick the 2 and 5x in the first place?
Oh, random.
Random?
Yeah.
Okay.
Other than, are you okay, Kai, that the 2 is a term being added to the purple term?
Yeah.
So we had to find terms that add. I just picked those 2 to start. So now I'm going to jump to, say, the 3 on the bottom, and I'll compare those. Is that your question?
Yeah.
2 more, please. Steve.
Do you not have to look at the 1 minus 3x before?
Oh, thank you. No one mentioned, so I forgot to talk about it. So Sadie says, let's compare these 2. So everybody in the room, 2 points for Sadie. As those 2 terms add, and x becomes increasingly negative, raise your hand. Is one or the other dominant? Like, does one of those 2 terms, the brown or the green, become increasingly less and less important as you plug in values of x that are increasingly negative? There we go. Your hand is raised, give yourself 2. Sydney, what would you say about the brown and the green?
The brown one is going to become less important.
As x becomes more and more negative. And the same would be true, honestly, if x were to become more and more positive. So we can say this, 3 points for Sydney, that really don't really care about the 1 either. So we can do that. Questions? Okay, on the bottom, it's not quite as obvious, but I have a little spreadsheet to kind of emphasize a key point. Here's the key point. If you have a term, so think of this as x. It's becoming increasingly negative. This is just -5 times that x. So you can see how that grows. This is 3 times that x cubed. And the idea is to notice how much more dramatically that grows than the other. In fact, in this spreadsheet, this is like Excel. When you get to 100 million, which is not really very negative in terms of mathematics, this value of the cube term is getting pretty big. The computer is being commanded to add them. Like it's telling it, add those 2 terms, add these together. Guess what? The computer gives up. It does not have enough computing power to add this red number to this red number. If you look at the result, there's no evidence that we even added this 500 million. The computer cannot do it. It doesn't have the computing power to keep track of a number that are so different. So this is completely dominant as far as the computer is concerned. It didn't even try. So if you're using very large numbers, watch out for that. The computer sometimes gives you the wrong answer. So, questions? Cool. So back here, number 13, we use that idea to say that on the bottom, the only term that really is going to make any difference is the 3x to the 7. The other 2 terms will become increasingly less and less important as x becomes increasingly negative. This idea is going to show up all year long, so talk with me if it's bothering you.
Is it just because it has a higher exponent than the others?
So you can memorize that fact, Sam, 3 points. That if you're dealing with what are known as power functions, something to a power, if they're just simple polynomials like this, just memorize that the higher power will always dominate.
Gotcha.
And it doesn't matter if x is going to negative infinity or positive, the higher power always dominates. We don't really take the time in this class to analyze any further than just kind of that spreadsheet to show you that that's true. Does that make sense? Yeah. 3 points. Please.
Why did you keep negative 5x to the second power if negative 3x to the fourth power dominates?
Oh, awesome. 3 points, let's see who can see it. Why am I keeping both of these? Because Spencer's right. I just finished saying to Sam that, hey, this higher power on the bottom is going to dominate, so I'm going to ignore these two here and just keep the 3x to the 7. Well, why did I keep both of these? Good work. Josh?
Because they're both in the set of parentheses.
Perfect, and being in the parentheses means they're multiplying, so they're not adding. You can only compare terms that are adding. You can't throw stuff away when you're comparing terms that multiply. How many noticed? 2 more, 3 for Josh. Did that answer your question? Okay. Anybody else? Oh, please.
If there were parentheses on the bottom, would you even be able to compare it as because?
Keep going.
Like, so if it was like the same thing but flipped, you would, like, it was on the bottom, you would be able to compare. Yeah.
Correct. Is that what you
Those
meant,
are also
Emily?
the same.
Is that what you meant?
Yeah.
Yeah, if there are 3, okay, they're not terms anymore, now they're factors. So if you have 3 factors that are multiplying, this comparison idea isn't valid at all. The idea only works if you're adding. Good work. 2 more. Cool. So it'd be good to hear. Awesome. Yeah, on the next line, write this, please. Equals the limit as x approaches negative infinity. Okay, right here, we no longer have any terms. There are no terms within the yellow box. There are no things being added to other things. They're all factors. They're all multiplying. With factors, you can mathematically spread them out to make things easier to see. So I'm going to spread it out a bit. I can multiply in any order I want because they're factors. So I could say, hey, wait a minute. Let's see, 5 times 3, that's 15. The 3 on the bottom. Then I'll have an x times an x, that's x to the 7. So that's really what I have, written in a much simpler form. Questions? And it was because they were all factors, I'm able to do that rearranging easily. If they are terms, you cannot do that. Like, you can't rearrange quite so easily. So. Oh,
Could
please.
you show one more time how you got to the...
Huh? So right here, these are all factors. There's a factor of x, 2 more for Spencer. A factor of negative 5. A factor of x times x. A factor of negative 3. A factor of x times x times x times x. You can rearrange them in any order and way you'd like. So I said, let's just take the factor of negative 5. Let's go ahead and multiply that by negative 3. That will give us 15. Then let's take this x times 2 more x's times 4 more x's. That will give us 7 x's being multiplied. That's your question. Anybody else? Solid. Okay, question for the whole class. Again, I gotta make sure you're following the logic, not just the steps. Way up here, there's a box. There's a formula. Put it in black. So we've got that black formula. That formula is being declared to mean the exact same thing as f of x. So this red box is an exact copy of the black box. It's just a different symbol, but it means the exact same thing. Red and black. Are you comfortable? Nodding is helpful, thank you. We're finding the limit of that red box, which means it's no different than finding the limit of the black box. Red and black are the same thing. Everybody with me? I need you to vote now. Don't say it out loud, I want to see how many know. Raise your hand if you can tell me. We know red and black are the same. Well, we've also got yellow. Are red, black, and yellow the same? Or are red, black, and yellow different? Hands up. Are they the same formulas or are they different formulas? Red and black are the same formulas. Is black the same as yellow? Hoping for more hands. That's looking pretty good. Looking good. Let's go Kate Hamilton. What do you think? So Kate says no. How many vote with Kate? 2 points, 3 for Kate. How many voted that they were the same? Show me hands. 2 points for voting. The correct answer is they are different. We threw stuff away to get from the black to the yellow. Like we discarded it, okay? However, what we said was the two formulas become closer and closer to being the same as long as the X you're plugging in is either getting increasingly positive or increasingly negative. Then the two boxes become closer and closer to being exactly the same. Black and yellow are technically never exactly the same, but they do get closer and closer to being equal as long as X becomes more and more positive or more and more negative. Questions? Okay, vote again on this one. So we've got the limit here. Remember, black and red are the same. So we've got this limit here in purple. And we've got this limit here in yellow, or let's go green, I guess. This limit here in green. Is the purple limit perfectly identical to the orange? Sorry, is the purple limit perfectly? Is the is the purple limit perfectly identical to the green limit? Hands up. Or are they different? We know that black and yellow are different formulas, but is the purple limit identical to the green limit? Hands up. Okay, hands are raised. We're going to click on somebody here. So 2 points if your hand is raised. JC, what would you vote?
I think they're different.
So JC says these two limits are different. 3 points for JC. Raise your hand, please, if you voted different. Okay, I already paid you points. Hands down. Who says they're the same? Anybody? Okay, if you have your hand raised now, give yourself 2 more. They are the same. Okay, the limits are identical. The limits are the same. The formulas are different. The limits are the same. The formulas are different. Because limit means you want X to become negative, whatever forever means, forever. So if we ever get to forever, they're the same. In the limiting sense, they are identical limits, even though the formulas are different. Is everybody with me? Okay. Awesome. So finding this limit now is not really too tough, because this is going to equal 1, and that's 5. So the limit of this formula is 5. So again, we're just doing XY pairs here. As the X value becomes increasingly negative, the Y value is going to become closer and closer to equaling exactly 5. So it never actually equals 5 exactly, but it does get closer and closer. So, questions? Please.
This kind of goes back to the beginning. I don't know if you explained it, but how do we know that we're pushing negative infinity rather than infinity?
Awesome. So that's just in the wording of the problem. 3 points for Nathan. They said use a limit to show if f has a left half horizontal asymptote.
Oh, gotcha.
Does that answer your question?
Yes.
Good question. Keep asking. You good?
Yep.
Cool. Please.
So where does the 2 and the 1 go?
So what we did is we said, okay, we're only interested in what is happening to the y values of f as the x values become increasingly negative. And if x is going to get more and more negative, when I add these two things together, well, this part's going to change as x changes. This part isn't. So when they add, every time x is bigger, the 2 is less important. So I say in the limit, meaning x is going to go forever, 2 is non-important. So I just discard it. Does that help a little? 2 more. Anybody else? Oh, please. Yeah.
So if it says in the wording of the question, a right half horizontal asymptote, does that mean it says positive?
Perfect. Perfect. 3 points. You good for that, Sienna? Please.
I just want to make sure I'm understanding.
Yeah, yeah.
So it equals 5 because the x to the 7th power divided by itself is just 1, so it's just 15 divided by 3.
Yeah, think of it this way, Samuel. Up here, I don't think that formula is really easy to analyze at all. It's messy, right? I can't really see what's happening. But because we figured out that this limit here, in this brown box, is going to be perfectly equal to this limit up here, we can do this easier limit. we can say, oh, it doesn't matter how big x is, this is just 1. So it's getting close to 5. Cool.
So it's approaching from the left side? Is that what you're kind of saying?
What we're saying is if you drew a graph, what you would see is, as you, remember, a graph is a bunch of points,
Yep.
and as you pick x's that are more and more negative, the y that goes with the x is going to get pretty darn close to a y value of 5.
Gotcha.
As long as x is getting very, very negative. What's happening over here, I don't have a clue. I've done nothing to figure out what's happening. Problem didn't really care, so I don't know. 2 more for Sam. Please.
If x was approaching a small number instead of infinity, would the green limit still equal the purple limit?
Oh, good question. Hold on. If x is 3 points for Brock, those 2 limits, right?
Yeah.
Those 2 limits are only equal if x is getting extremely positive or extremely negative. Nothing else applies. If we were finding the limit as x approaches 5, everything we did is invalid. Because our assumptions were all based on x becoming extremely negative or extremely positive, not x getting close to even 5 million. Does that answer your question? 3 more. Anybody else? Oh, please, Kate.
Would the answer to the question just be 5?
So the answer would be, we've got 5 there. Oh, sorry, can you read it? So now we got to have a conclusion. So you should still write a conclusion. You should say, therefore, f of x, come on, x. F of x has a left horizontal asymptote at an x coordinate of, oh no, my bad, sorry, y coordinate, don't mess that up. There's a horizontal asymptote of y equal 5. Question. And now we're finished. Please.
So would we do this? Would we do these like steps any differently if it was a total infinity?
Oh, outstanding. 3 more for Spencer. Everybody look, I see your eyes again. Look up. This problem is only using simple polynomials, like a ratio of polynomials, power functions. If they're simple power functions, the result is always identical whether you're doing left or right. So that's kind of handy. But I warn you, the next worksheet has some non-power functions. Throws in some exponential and logarithmic functions, and they don't behave quite as symmetric. Like, they're not hard, just have to memorize a few different facts.
So the only difference, if it's like doing a left half horizontal or right half, is that it's either getting more and more negative or more positive. But everything else, like,
Is identical, perfectly the same. The signs and everything are actually changing with negatives, but it turns out that with power functions, the highest power still is dominant. Whether it's extremely positive or extremely negative will vary, but it's still the most dominant. Good question. 2 more. And again, just a warning that the next worksheet will have some exponential log functions, which aren't quite so straightforward, but they're not bad. Just got to memorize something different. So. Cool. All right. Any other questions here before we stop the video? Solid. Okay, so that one's done.